Okay, so this video is going to cover a few details on what exactly is the wave function now that we've become acquainted with our wave function psi, and we'll also talk about the Born interpretation, which is how we can make the wave function useful for us in our quantum mechanical calculations. Okay, so first off, what is the wave function psi? Well, the wave function is, as we've seen before, we can think of it as a variable quantity that mathematically describes the wave characteristics of a particle. We've seen that this function can be a complex function. Okay. The problem with having a complex quantity, however, is that it can't be measured by any physical instrument that we have. So we really shouldn't be asking ourselves, what is waving and what is it waving in? That's not a question that we can have a meaningful answer to. All right, well then what can we say about our wave function? Well, it's not to be thought of as a physical wave, okay, so we can stop trying to picture that in our heads of our wave function behaving as a physical wave. It's really just an abstract mathematical quantity that gives information about the state of our system. So we've talked about this before with our first postulate, how our wave function tells us everything we need to know about the state of our system. Okay, but that's really all it's telling us, right? It turns out that the atomic orbitals and molecular orbitals that you're familiar with from Gen Chem and organic chemistry, those are actually examples of wave functions, and we'll see that later on in the course. Okay, so what information does the wave function give us that's actually useful for when we're doing measurements? Okay, that's what we're really interested in right now. That's where something called the Born interpretation comes in. Now, shortly after Schrödinger discovered his Schrödinger equation, Born postulated that psi star psi dx is the probability that the particle is located between the region x and x plus dx. Okay, so this little infinitesimal space, region of space. Okay, so here we have our Born interpretation, psi star psi dx. You'll also see that written many times as psi squared dx. Okay, we can treat those equivalently. That equation gets the label of our probability density. Okay, so we're talking now, moving in terms of talking about probabilities of outcomes rather than certainties like we were able to do in our classical discussions of things. Okay, so if we look at this equation here, we have our complex conjugate of our wave function times our wave function. Okay, so let's say our wave function's complex, right? We already said that that's troublesome because we can't measure a complex quantity, right? So if we take a complex number, so a complex wave function, times its complex conjugate, it turns out that that gives us a real number. Okay, so psi star psi is real. Okay, and that is beautiful for us because then we can measure a real value. Okay, so that's why when we start getting into doing calculations with this wave function to get information about physical quantities, you'll see that we will be dealing with a situation where we have that psi star psi in there. And that is, again, because that quantity gives us a real number that we can measure. Okay, so just a little bit further look into this probability distribution. So here we have a beautiful little plot of just a general probability distribution. So this is a plot of a wave function squared. So this green curve is a plot of a squared wave function. So our probability distribution. Okay, and then this slice here is just representing that area x to x plus dx that we're interested in calculating the probability for. Okay, so that dx, okay, is really just representing that space over which you want to obtain the probability for that specific region in your function. Okay, so and just to tie this back to that concept of normalization that we're getting into as well. So the reason that we like to normalize our wave functions or like to work with normalized wave functions is because, again, incorporating this idea of the Born interpretation and that idea of a probability distribution, what normalization tells us is that if we integrate our probability distribution over all space or over whatever bounds you have for your particular system, okay, that value should equal 1. Okay, so if you have a normalized wave function, you calculate that integral, that probability distribution. If you integrate that probability distribution, the probability of finding your particle somewhere within your bounds of your system must be 1. Okay, and basically that just assures us that our particle is somewhere in our system. Okay, because the question becomes really uninteresting if there's no particle in there for us to look at. So normalization basically just assures us that we do have a situation where we have a particle somewhere, right, in within our bounds. Okay, so now we're kind of moving from this classical idea of being able to talk about things with certainty, okay, make measurements with certainty, make predictions with certainty, and moving into the quantum mechanical realm, which is really statistical in nature. Okay, so even if we know the state of our particle or our system, okay, we can't predict the results of a position measurement or any other kind of measurement with certainty. Okay, what we can do is we can really only predict the probabilities of various possible results. Okay, so we're just moving from this realm of certainty in our classical world to the realm of uncertainty and probabilities of things happening when we enter into our quantum mechanical realm. Okay, that's it. Hope that was helpful. Thanks.